Hello. We will be closing out the conference. I'm going to read a paper that was sent in by Father Paul Haffner. He studied physics at Corpus Christi College in Oxford and defended his doctorate at the Gregorian University under the title Christian Faith in God the Creator in Relation to Modern Science, according to the works of Father Stanley Jáki. He's still at the Gregorian. He was teaching this week and couldn't be here. He is the president of the Stanley Jáki Foundation since 2010 and works very closely with Antonio and others to keep promoting the work of Father Jáki. So I'm going to have time to read a little less than half of his essay before we need to head out to the Archabbey. By Father Paul Michael Haffner. Science has its own particular method, which consists of the investigation of the universe by observation, the formation of a hypothesis which is seen as objectively more plausible than other hypotheses, and the use of mathematical tools for the description of scientific theory. Scientific method restricts itself to counting, measuring, and weighing, and is therefore not about persons, personal commitments, human destiny, or responsibility. Thus, the scientific method, and indeed science itself, has a limited competence, a point to which we shall return later in this chapter. Nevertheless, science has its own particular ethos, something which goes deeper than usefulness or expediency. Science is a search for truth, and as such needs to be conducted in an atmosphere which is free, open, and honest. Hence, science is subverted when it is made the slave of a political system, such as happened in Nazi Germany and in the communist Soviet Union. Science has had an inner coherence for the past 400 years, which makes it historically and socially unique, as compared with other branches of learning. The consensus among scientists is far greater than that among philosophers, literary critics, and historians. Historically, science, which came to an aborted birth at 7 great cultures, Chinese, Hindu, Maya, Egyptian, Babylonian, Greek, and Arabic, generates an increasingly universal consensus since it came to a viable birth only once in late medieval Europe, between the 13th and 16th centuries. Socially, science is unique, stretched as it does beyond a family or a state. From the cognitive point of view, science is also unique because of its special object matter, the quantitative patterns of material reality. It is in this light that one should see the dependence of science upon common sense judgments, both with respect to interpretation and to utilization. The basic reason for a necessary recourse to common sense in science lies in relating abstract mathematical formulae to physical explanation. Furthermore, science has a pluralistic conceptual matrix. This stems from the need to explain successfully physical reality in modern physics. Here, one of the great landmarks is the principle of complementarity, according to which all particles, not just light, have wave properties, and all waves act in certain circumstances as particles. Hence, both aspects must be taken into account in the conceptual framework which constitutes the wave-particle duality. Nevertheless, this pluralism lies only within the quantitative dimension. An extrapolation to philosophical pluralism on these grounds is unjustified. The incompleteness of science. Science, seen as a content of human thought and as a method of human activity, appears to be both convergent and divergent. Science makes such progress that within one discipline, say physics, different discoveries shed light on each other so as to encourage scientists to look forward to a unified theory. This convergence, Jáki warns, is not the whole story, for theory and experiments do not always point in the same direction. Sometimes the converging lines of physics suddenly veer away from one another and new avenues open up, the direction of which no one could guess with any certainty. This happened with the advent of quantum physics, which sharply contrasted with classical physics. Moreover, there is still no unity between quantum theory and the theory of relativity, the two main pillars of modern physics. Another major feature of the incompleteness of science appears through its having passed through three views of the world, namely as an organism, a mechanism, and a pattern of numbers. Jáki finds an essential incompleteness in each of these worldviews as utilized by physics. The world, so Jáki recalls in great detail and in various contexts, was conceived as a gigantic living being by the ancient Greeks, by the Arabs, and by the medievals up to a point. This view reappeared even in such modern writers as Goethe. Jáki attributes great importance to Socrates in the development of an organismic approach in science. Socrates defended purpose with an eye on the physics of the Ionians and of Anaxagoras, which dealt only with the succession and configuration of events. However, by reacting against mechanism and quantities, the opposite danger ensued from an over-exclusive attention to purpose, namely the extremist stance of seeing purpose everywhere. Plato further developed an organismic view of the cosmos, for in the concluding part of the Timaeus, an animistic and pantheistic account was given of the universe in terms of the human body. The organismic model had the limited advantage of giving a unity of perspective to the world and to science, but this was a priori and artificial. Organismic physics viewed nature as full of volitions which were under the control of the great animal, not under man's control. The view imposed an essential incompleteness to science by allowing only qualitative purpose questions in science. The theory thus failed physics in questions of details and gave a view of reality which was seen to be more and more unsatisfactory as science advanced. Man had to look deeper and consider the beautiful display on the stage of nature a poetic disguise and look for the ultimate reality in the ugly, soulless mesh of ropes, pulleys, and levers found backstage. Unfortunately, when the organismic worldview was superseded, for 3 centuries, machines were to be idolized with as little second thought as had been the concept of organism for over 2,000 years. In the Middle Ages, there came the intervention and rapid development of mechanical clocks. There was, correspondingly, a greater willingness to describe reality in terms of clocks and other machines. This inspired the search for mechanical laws everywhere in the cosmos. The mechanistic worldview lasted only about 3 centuries, from the early 17th century until the early part of the 20th century, and generated the unfortunate a priori tendency to mold scientific explanation on mechanical pattern. Light, heat, electricity, magnetism, and planetary motion were all seen as the functioning of little machines. Jáki notes that the constancy of speed in special relativity made meaningless that application of mechanism in explaining light phenomena. General relativity made it equally meaningless mechanical explanation of planetary motion. Planck's quantum theory dissolved into a haze the sharp contours of the mechanistic conception of the atom. No longer could one think that the imperfections of physics were getting less and less important. Thereby dashed were the hopes for a complete scientific vision of the cosmos. Like its predecessor, organismic physics, mechanistic physics became a creed, a state of mind, and as such, brought about its own demise. The mathematical limits of physics. Mathematical basis of limits. It was not until the advent of modern physics in the early 20th century that the world became seen as a pattern of numbers, but in a way different from the Pythagorean view of the world. Jáki notes that the great extent to which pure numbers are very important in atomic theory, astronomy theory, and the study of elementary particles. This use of mathematics is different from the one in classical physics view, where it was subordinated to a common sense and often mechanistic picture. For classical physics, mathematics was seen only as the key to ordering of the facts of nature, not as the source of the facts of nature. Now, in modern physics, highly arbitrary mental mathematical constructs are used in such a way that these constructs cannot be directly related back to physical reality. Finding a picture for the construct is no longer of great concern. In Jáki's words, modern physics indeed went all the way in embracing the abstract world of mathematics and renouncing unequivocally the desirability of visualization in the physical method. Consequently, in the early 1930s, it was hoped that theoretical physics would soon come into possession of a definitive, all-inclusive mathematical formalism. This hope was based on a type of faith in mathematical description, analogous to that which supported an organismic or mechanical worldview, even if these latter are less apt descriptions than the mathematical. The all-embracing mathematical synthesis has not been found. There seem to be mutually exclusive groups of phenomena underlying quantum mechanics and the theory of general relativity. For Jáki, the most conclusive proof of the mathematical world model in science stems from Gödel's two theories of incompleteness. According to these, no sufficiently broad, non-trivial set of arithmetical propositions can have its proof of consistency within itself. Although this seems to be confined solely to mathematics, Gödel's work centered on the system of integers, there is a meta-mathematical corollary. Applying this theorem to the whole gamut of mathematics, the inconsistency cannot be proved within any set, but rather another set of assumptions is needed, a meta-mathematics. Yet to show the consistency of this meta-mathematics, a further meta-mathematics is required. Meta-mathematics all the way down. So the progress continues in an endless regression, which means that each set of rules for the mathematical symbols points beyond itself. Moreover, the meta-mathematical content of Gödel's theorem means that no mathematical description of physical reality can have its proof of consistency within itself. Thus, even in the pure thinking of theoretical physics, there is a boundary present, as in all other fields of speculations. Since scientific cosmology is highly mathematical and this mathematical apparatus must be subject to Gödel's theorem, it follows that there can be no a priori mathematical synthesis of the cosmos. Thus, no scientific cosmology can have its proof of consistency within itself as far as mathematics goes. Jáki nuances his position by stating that Gödel's theorems do not preclude the possibility of a physical theory covering all physical phenomena. In other words, ultimate cosmological theories may be true, but never necessarily true. According to Jáki, Gödel's theorem does not mean at all the end of physics. It means only the death knell on endeavors that aim at a final theory, according to which the physical world is what it is and cannot be anything else. Gödel's theorem does not mean that physics cannot come up with a theory of everything. They can hit upon a theory which, at the moment of its formulation, would give an explanation of all known physical phenomena. But in terms of Gödel's theorem, such a theory cannot be taken for something which is necessarily true. Apart from Gödel's theorem, such a theory cannot be a guarantee that in the future nothing essentially new would be discovered in the physical universe, which would then demand another final theory, and so on. Regress to infinity is no answer to a question that keeps generating itself with each answer. For Jáki, the all-important implication is that scientific cosmology can therefore never be a threat to the fundamental contingents of the universe. Jáki first discussed the cosmological significance of Gödel's theorem in The Relevance of Physics in 1966. After its first publication, the work was reviewed in more than 100 different periodicals. None of the reviewers noted pages 127 to 129 in the book where Jáki made this connection. Since 1966, there has been little response from scholars. This lack of reaction stems, according to Jáki, from the fact that the climate of thought in our times is not at all favorable for recognition of reason's ability to bring within sight the contingency of the universe and its raison d'etre. It's having been created by a being truly necessary. Jáki further developed his cosmological extension of Gödel's theorem in subsequent books. The first of these was the text of his Gifford lectures, given at the University of Edinburgh in 1975 and 6, which appeared under the title The Road of Science and the Ways to God. Again, he discussed Gödel's theorem in physics in the book Cosmos and Creator in 1980. Jáki then devoted an entire chapter, Gödel's Shower, shadow to the same argument in a series of lectures given at Oxford in 1988, later published under the title God and the Cosmologist. His application of Gödel's theorem to physics was dealt with in several other works. One was his synthesis of philosophy, Means to a Message, a treatise on truth. The other, his intellectual autobiography, A Mind's Matter. Published by Eerdmans, a publisher with worldwide distribution. The well-known theoretical physicist Roger Penrose summarizes Gödel's theorem. However, he does not notice its relevance for physics, even though he speculates at length about a still unknown form of quantum theory in order to claim a final theory is possible. And I will stop there. Thank you, and this will be in the proceedings.